of all. So I'm Dr. Richard Law. I'm a lecturer in chemical engineering at Newcastle University. I'm going to be chairing the workshop this morning on behalf of the UK National Heat Transfer Committee, which is chaired by Tassos, who will give a brief introduction in a moment. So the running order for today, you should have seen the program in advance anyway, but Tassos Karianos will give a brief introduction to the UK National Heat Transfer Committee first of all. Angela will then say a few words about the Supergen Energy Storage Network. So this is a joint event between our committee and the Supergen Energy Storage Network. We then have Mark Linder from the German Aerospace Centre, who's going to give his presentation, followed by a Q&A session. And then Adriano from the University of Birmingham will give his talk, again followed by more discussions. So Tassos, if you'd like to share your slides now. So hopefully you guys all know Tassos anyway, but he is a professor at Brunel University, and he's the chairman of our National Heat Transfer Committee in the UK. So over to you, Tassos.
Thank you, Richard. On behalf of the committee, a very warm welcome. Good morning to all of you. I see we have a lot of people attending. So this is I'm very pleased with the turnout, and I'm very pleased with the interest that our first workshop this year has attracted. We have done live workshops before, but due to COVID, this year we were forced to have this Zoom presentation. So I'm again very thankful to Birmingham for organizing this with us. On behalf of the UK National Heat Transfer Committee, very warm welcome. I'd like to say just a couple of words about the committee, and then I'll pass you back to Richard. If we could move to the second slide. The UK National Heat Transfer Committee was established in 1982. This was in response to the decision by the Assembly of the International Heat Transfer Conferences. This is an international assembly from all major universities in the globe. They get together, they organize every 4 years the International Heat Transfer Conference. They maintain contacts and support any activities in heat transfer. So the UK at that time was called to participate, join in, and in 1982, the committee was formed. Originally, it was formed as a joint committee of the Institution of Mechanical Engineers and the Institution of Chemical Engineers. And the representatives from these institutions were nominated then to represent the UK at the International Heat Transfer Conferences Committee. The founding chairs were Professor Jeff Hewitt from Imperial College London and Professor Hugh Simpson from Strathclyde University. The current members of the committee, and there's about 15 of them, come from UK universities and industry. So we are based across the whole of the UK with people from academia and from industry. The industry is usually companies that relate to the heat transfer science and engineering, and they join us to support the work that we do. So what is our mission? The mission is to advance the development and exchange knowledge in the heat transfer across the whole of the UK. We wish to promote excellence in the heat transfer education, which includes research and practice. So we embrace both teaching, we embrace, of course, research, and we embrace practicing aspects of the heat transfer science. We facilitate the exchange of relevant knowledge in heat transfer. We promote collaboration between industry, universities, and government. So we are the vehicle sometimes for some communication between industry, university, government, and the professional bodies. And we facilitate through some workshop and seminars the public understanding of technical issues that relate to the heat transfer science. And with that, we hope to raise the international profile of the UK heat transfer community. So our members are very busy, engaged in all of this, and that's why you see Richard this morning working with Birmingham to facilitate this workshop. Other things that we do, every 2 years, we hold a National Heat Transfer Conference. This is usually attended by about 150 people. This is the premium forum in the UK to present work that relates to heat transfer. And heat transfer, of course, embraces aspects of energy as well. So it's not just the specific aspects of heat transfer, but anything that utilizes, depends, and promotes heat transfer is part of our conference. We organize workshops, and this is an example. We usually do it twice a year. We involve academia, research, and industry. The last one we had was in Derby, and the title of that one was Heat Transfer Research, Education, and Practice in the UK. So we had panel experts talking about the hot topics, let's say, of research in heat transfer. What shall we do with universities and how it's best to include heat transfer in the curriculum, and some aspects of advances in practice in heat transfer that companies are doing, like heat transfer and enhancement, for example, and where that is driving the heat transfer community. For your information and for dissemination, if you have people that are involved that could submit here, we offer best prizes for the best PhD or MH thesis that relates to heat transfer. We offer the Jeff Hewitt Prize for the best PhD thesis on a topic relating to heat transfer. So if you would like to, if you have people to recommend that they have just done a nice project in their MH thesis or the PhD thesis, or one that they're just about to do, please let us know. At the same time, if you know of a PhD student that just graduated and the project relates to heat transfer, they might be eligible for the best prize for a PhD thesis, and this is a very prestigious prize for PhD graduates. At the same time, we'd like to recognize the contribution of our colleagues, both in industry and academia, for continuing to support heat transfer. And these years, I'm very pleased to say that these years, the prizes for these years have been awarded to Professor Brian Launder from Manchester University and Professor David Kenning, Oxford and Brunel Universities. With that introduction, I don't want to take any more of your time. I want to wish you a good workshop. Thank you again for attending on behalf of our committee, and pass you on to Richard to continue. Thank you very much.
Thank you, Tassos. So just a note to everybody, I have popped my email address and also the website of the committee into the chat. If anybody wants any more information, you can send me an email. For example, if you want information on the prizes for the best PhD thesis or the best master's thesis, etc., please send me an email. And I also encourage everybody to go on to our website and sign up for the newsletter. So we send out a newsletter. It's not very often, it's maybe once every 3 months, something like that. And we send out all information about prizes and about the UK Transfer Conference, etc. So I encourage everybody to either get in touch with me or sign up on the website.
Richard, this includes MSc thesis as well. So
yeah,
in this group, I think we need to point out that master students are also eligible to apply. Yep,
that's right. So if you want any more information about that, just send me an email, and I can put you in touch with who is dealing with that on the committee. Okay.
Thank you very much.
Thank you. So next up, I think Angela's just going to say some words about the Supergen Energy Storage Network.
Hello, everyone. I'm Angela Finger. I'm really glad to see so many participants today. I would like to welcome you on behalf of the Supergen Energy Storage Network Plus and give you a quick introduction to who we are and what we do. So for those who are not aware, our network is led by a Professor Yulong team and University of Birmingham, along with the support of a multidisciplinary team of 19 investigators from 12 UK institutions. And we are funded by EPSRC. We have strong industrial support with 34 project partners and 2 million in kind support. We started on September 2019, and it's a 4-year, we have funding for 4 years, and we hope to extend that. Our vision is to connect stakeholders across the whole energy community while advancing UK energy storage research. So in addition to thermal storage, The Network Plus covers technologies ranging from electrochemical to thermal and mechanical. The network aims to accelerate and support the interaction between those different sectors to deliver significant impact and research excellence, while supporting early career researchers and making sure that equality, diversity, and inclusion is an integral element across all fields. So that is all from me. I will pass you now back to Richard, and I hope that you enjoy our webinar today. Thank you very much.
Thank you.
I also actually want to add that I will put the link for our website, and please feel free to subscribe to our newsletters. And also we send regular emails with opportunities for industrial stakeholders, for early career research, for academics. So please subscribe and follow us. Thank you.
Thank you very much. Okay, so we're only going to be about 5 minutes behind time, which I think is quite good for one of these online seminars. So Mark, if you would just like to load up your slides, and I'll briefly introduce you. So yeah, so Mark Linder is from the German Aerospace Center. He's going to give a talk on reversible gas-solid reactions for high-temperature thermal energy storage. So thank you, Mark. Thanks for agreeing to present today. If anybody has any questions during the presentation, you're welcome to pop those in the chat, and I'll keep an eye on the chat. And at the end, during the question session, I can either read out those questions or invite you to ask the question yourself. I also ask that everybody mutes their microphones during the presentations, which I think everybody has anyway. But yeah, so if you have any questions as the talk proceeds, please pop them in the chat, and I'll keep an eye on that while Mark presents. So over to you, Mark, and thanks again for agreeing to present here today.
Okay, Richard, thanks a lot for the introduction, and of course, a great thank to the organizers for having me here in this workshop. The question was if I could talk a bit about thermochemical energy storage, especially for high temperatures. I changed the title a bit. It's about reversible gas solid reactions for high temperature thermal energy storage. My current position at DLR is I'm acting head of the department thermal process technology. This is more or less part-time of my job by heart, and this is the second part of my job. I'm leading a group called Thermochemical Systems in this department. Regarding the content of my presentation today, I would like to start with some very generic and schematic considerations on thermochemical energy storage. I will then have a couple of slides regarding one example we have developed the last years. We call it thermal upgrade as one specific application potential, technological potential of thermochemical energy storage. At the end, I would like to give you a quick insight in who we are, the group, what we do besides thermal upgrade, and of course, I try to summarize my presentation at the end. The department, Thermal Process Technology, works with around 40 to 50 scientists, basically on all technologies to store thermal energy at high temperatures. So you can say from the left, Dr. Stefan Zunft and his group, they work on sensible storages with solids, so-called regenerator or solid state storages, and also a bit on high temperature heat exchangers. Of course, you can reach extremely high temperatures there, and at these temperatures, you also have the chance that you can avoid any metallic heat transfer structure. So there are clear advantages of this technology, and this is of course also the reason why this technology is mature. In the light blue second group, Dr. Thomas Bauer and his colleagues work on thermal systems for fluids. These are mainly molten salts, so nitrate salts or chloride salts. Of course, these fluids are pumpable, so you can scale on one side the power level of your heat exchanger, and on the other side, just the volume of your storage tanks, so capacity and power level independent from each other. Up to 560 degrees Celsius. This is also a very mature technology. It's commercial in the context of CSP. You definitely know that. Besides these very mature technologies, we have a almost as mature technology, I would say. The group of Dr. Dan Bauer They work on phase change systems, mainly salts. And of course, due to the low thermal conductivity of the salt, of the solid material, we need sophisticated heat transfer structures inside of the storages. You see one of these pictures here. So also this technology has reached something like ton scale, 30 tons. The picture here on the right, it's probably a bit small. It's actually a very new one where this technology is now installed in a real industrial site. The sophisticated structures I mentioned, they are available in kilometer length, so as tube bundles. Those colleagues, as I said, work with high temperature PCM, 140 up to probably 300, 340 degrees Celsius. And now the question arises, if these technologies are mature in ton scale, what is the role of thermochemical energy storage, especially in the context of high thermal energies, high temperature thermal energy storage? This is the main motivation of my talk today. I would like to talk about specific advantages, because all of these technologies have their advantages and disadvantages, and it's clear that only depending on the later application, you can decide whether this advantage or disadvantage is important or not. Okay, if you say, okay, what are thermochemical energy storages? You might take a textbook, and in this textbook, you might find something like this. It's more or less the same structure I was showing before in the last slide. They will say, okay, we have some sensible heat storage possibilities, solid and liquid in different temperatures. We have latent, and then we have heat absorption and heat of reaction. And in most of the textbooks, even those two are somehow summarized with the expression thermochemical energy storage. And then you will read a bit, and I promise it's clear they will say that the energy density increases here, and the advantage, the specific advantage of these so-called thermochemical storages is that they can reach high energy densities. This is definitely true on a material scale, but it's of course, it still has to be proven on a system scale. Besides that, if you read a bit longer, further in these textbooks, you will find the expression, yes, this storage technology is free of losses. So you can store thermal energy for long periods. I would try to modify this expression a bit and give you a video here. This is a picture of two coupled chemical reactions. One is on the left side and one is on the right side, and these are three identical. If we now make a video of it, we can see that as soon as my colleague is opening the valve, she actually decides when the exothermal reaction on the left, so the temperatures tend to the red, and the endothermal reaction on the right, the temperatures tend to the blue, is initiated. It's under her control. So it's a controllable heat release, if you want. But it's a bit more. Of course, you could imagine that my colleague does not open the valve completely, but only half. Then you could also control the thermal power, which is generated by these chemical reactions. So you, as a user, you get control of your thermal energy. It's the only technology where thermal energy is stored at ambient temperature. Okay, this is the second advantage, free of losses. But I think there is a third one, and this is actually the one where I am from a scientific point of view interested in. And this is where I want to focus now the presentation on. For this purpose, we need to dig a bit deeper into this generic expression thermochemical storages and differentiate between a sorption process. The sorption process is shown here. This equation could also be from the textbook. It states that there is a compound, you add delta H, thermal energy, and you shift the equilibrium to the right, thereby releasing a gas beam, right? And examples for these sorption materials would be zeolite, silica gels, or even liquid absorbency. I'm sure you know all that. The interesting thing is, if you have a look on the right side of this slide, there's a very schematic, I apologize for that, but a very schematic diagram. And it states that on the y-axis the pressure, on the x-axis is the temperature. And if we assume we have a given pressure, we have several lines here. These lines correspond to the state of charge, or actually the coverage of the gas, which is adsorbed on the surface of, for instance, our zeolite. And these lines state that, of course, if we increase the temperature for a given pressure, we can dry our surface. If we do not increase it that much, we have a larger coverage there. Or in other words, we talk about a gradual charging of these thermochemical systems based on sorptions. We can only have a large energy density if we have a completely or almost completely dry material during charging, and a almost completely, let's say, charged material with gases adsorbed on the surface after the discharging process. Or in other words, either we have to play with temperatures, high temperature for charging, low temperature for discharging, or we have to adjust pressures, gradual charging. This is a bit different if we talk about chemical reactions, in this case, gas-solid reactions. The reaction equation here, generic, can be the same. The difference is that now this solid material A undergoes structural changes. It's a chemical reaction. There's a new compound formed. This could be, for instance, the case for calcium hydroxide. If you add thermal energy to calcium hydroxide around about 500 degrees Celsius, this is what you need. You dissociate it to calcium oxide, a new chemical compound, and water vapor. And in this case, the diagram on the right side looks a bit different. Yeah. Again, pressure, this is temperature. This is now 1 divided by temperature, so to the left is hot. But we have now only one single line. Or in other words, if we say we have a gas pressure available, constant gas pressure, we only need a slight increase in temperature or a slight decrease in temperature in order to reach full conversion, completely converting the whole material and thereby absorbing or releasing the maximum possible thermal energy. Okay, what does this mean? Or as probably before that, I have an example here. This is not a good thermochemical storage material, but it's, I think, a nice diagram to explain what I mean. My colleague Margarete Richter was publishing a material screening for salt hydrides. This is the thermogravimetric analysis measurement, and you can assume that the water vapor pressure is constant. We start at high temperature, position 1, we reduce slowly the temperature, and at a certain temperature, 130 degrees, for instance, we see a clear step, an increase of the mass, which can be calculated to 1 mole of water, which is attached, reacted with the magnesium bromide, actually. Then we reduce the temperature further, and then we have a clear second step at, let's say, something like 75 degrees Celsius. The backward reaction, we increase the temperature, everything is the same, gas pressure is the same, we increase the temperature, we need something like 90 degrees Celsius to release the first mole of water, and then again 140 degrees Celsius to release the second mole of water. So the theory from the last slide, one distinct line, is now that we have 2 lines, on the first mole and the second mole of water, and we have, of course, an hysteresis here, which makes this material not that attractive for thermochemical energy storage, but it proves that we have these distinct lines. Okay, so what I would like to discuss and probably to introduce is a kind of a new classification. We say this is the same diagram before, I just changed a small thing. I just switched the position of the latent heat and the heat absorption. The idea behind that is that this is scientifically not perfectly correct, but from a technical point of view, I think that could be helpful. We have the latent heat where the melting and the solidification happens at a constant temperature. It's a physical phase change, but with full conversion. And the same is true for the heat of reaction. In this case, of course, it's not a chemical phase change. It's a chemical reaction, but just as using this analogy, we say it's a chemical phase change. The complete reaction occurs at the same temperature, full conversion. Okay, what does this mean? Again, a schematic drawing on the right, temperature versus energy content. It's clear for sensible storages, we can say yes, it's clear. The higher the temperature, the charging temperature, of course, the higher is the energy content in this type of thermal store. Can state yes, of course, if there is an application that limits my maximum temperature, some material properties or something like this, but I want to reach high energy densities. I want to store more energy, then you can say yes, all these latent storage materials, they have a sensible part at the beginning, they're solid here, and assuming the heat capacity is the same, of course, this is not true, but as a schematic. At a certain point, we have this physical phase change, and of course, between these 2 temperature levels here and there, the latent store can store more energy. And if you say, okay, yes, I have heard in a workshop, a presentation from DLR. They mentioned that this is comparable to the latent, thermochemical is comparable to the latent, and there in the textbook I see that we have higher energy density. You could probably draw it like this. It's clear we have a certain reaction temperature, and the energy we can store in this chemical reaction might be a bit more in comparison to the latent unit. This is only half of the truth, because the interesting thing is now, since we have only one straight line, we can of course adjust the reaction or the storage temperature by adjusting the gas pressure, the reaction gas pressure. And thereby we can increase the storage temperature, for instance, for discharging. What does this mean, storage temperature? I mean, I was very generic here. I had one example, magnesium bromide was not a good example. These are systems we have actually analyzed in my group during the last years. We can start at very high temperatures with metal oxides reacting reversibly with oxygen at temperature above 800 degrees Celsius. And also there, this dependency of the reaction temperature from the gas pressure occurs. So we can have temperature adjustment during the storage operation. We have calcium hydroxide, for instance, or magnesium hydroxide. They differ extremely. Calcium hydroxide is an excellent material for utilizing this, call it advantage. Then we have salt hydrides. This is the example I will continue with in the next couple of slides. And then in blue, we have metal hydrides. So this is also true, partially at least true for metal hydrides, or even complex hydrides, so systems that react with hydrogen. So you can basically decide what is the temperature, in which range I want to start, I want to work, and you can also decide what is the reaction gas I want to choose: oxygen, water vapor, and hydrogen. This is what we have done so far. So I would add as third specific advantage the adjustment, the controllability, not only of the when you release your thermal energy, or at which power level you release your thermal energy, but you can also at least partially control at which temperature level you release your thermal energy. And this is the content of the example recent work from our lab. Starting with the problem motivation challenge, you can say, okay, let's think about waste heat here in blue. There's a certain temperature, there's a certain time when this waste heat occurs, and the reason why this is waste heat and not thermal energy that we can use could be because we cannot use it at the moment. So we think of a thermal store, we charge it and discharge it, and then later on, we can use it at slightly lower temperatures. Of course, we have to charge it and discharge it with temperature gradients. This is one possibility. The other one is, okay, no, it's not a time, it's a temperature level, it's the quality of the energy, of the thermal energy. So let's think of a heat pump, of a high temperature heat pump. Let's immediately take it, pump it to a higher temperature level in order to reintegrate it to my process. These are two different units. The one is able to store it, but not to upgrade it. The other one is able to upgrade it, but has no storage possibility. What we call thermal upgrade is now the combination of these two units, if you want, these two components. How does this work? We have again this equilibrium line. Now you see it's not a generic pressure, it's pressure of water. Yeah? We have a solid material here reacting with this water vapor as a salt hydride. And of course, we can condense and evaporate water along this water vapor line here, which is again in a schematic drawing, also a straight line in this so-called Van 't Hoff plot. So the operation would be now, we adjust a certain pressure, P1. At this pressure, we have a reaction temperature here shown as T low value. Yeah? At this temperature, we charge our solid material, dissociate it, generate water vapor, and then of course we do not want to increase the pressure, we want to maintain the same pressure, so we have to condense it in a second unit which is connected to it, and of course the heat of condensation we have to release to the ambient or higher temperatures, roughly 100 millibar as absolute water vapor pressure if we want to reduce it to the ambient. And if we say now, yes, okay, we have some waste heat, 60, 80, 100 degrees Celsius available, we can evaporate water, have a higher pressure, and then have a higher reaction temperature in our solid material. So in this case, we would try to utilize waste heat, not as heat in order to reintegrate it, but as driving force for our internal chemical heat pump, which we call thermal upgrade. My colleague Jana Stengler was doing a lot of investigation here, did her PhD on this topic. Here you see a first work, beginning of her PhD, where she was analyzing the exact equilibrium of this strontium bromide water material. You see here on the right a comparison between the theoretical line and our experimentally determined equilibrium line. And what you also see is that in the relevant pressure range, we have temperatures between, let's say, 160, 170, and up to 270, 280 degrees Celsius. As I said, you could adjust this by changing your solid. We have not only the problem, like the PCM colleagues, that we have a low thermal conductivity of the solid. We have it a bit more severe. Our solid is in porous bulk, so the thermal conductivity is even lower. So we need some ideas, some measures in order to improve the transfer of thermal energy inside of this bulk. And I mentioned it in the introduction that our colleagues, Mikey Johnson, for instance, from the PCM group, they have developed this fin structure here you see on this picture. They use it now in kilometers length. The idea is that we have a stainless steel tube inside. The stainless steel is able to withstand some pressures we need for evaporation or condensation of water, for instance. We have aluminum fins, of course, to distribute the thermal energy into the bulk. And we have these clamps that actually connect these two parts of this heat exchanger or heat transfer measure. And we said, okay, if this is possible for a melting, a solidification technology, it should also be possible for a solid that is releasing a gas and absorbing it later on. For this purpose, we need a filter. This was just put around these fins, and the volume, the white volume inside of these heat transfer structure was then filled with the reactive material. This is how it looks, or it looked. This grayish part here is actually a thin filter. There's nothing this filter has to withstand except the pressure drop due to gas transfer. And then we see here the aluminum fins, and we see this white part, which is the solid or porous solid material, strontium bromide. You can calculate the energy density for this unit here. This is something like 70 kilowatt hours per cubic meter. We can have something like 4 kilograms per meter of tube. And the reason why is that it's not that impressive. You might see here in this zoom, there is a large porosity, of course, between this material or within the bulk. And of course, this porosity has a direct impact on the energy density. So we could try to compact it, but this was not the focus of this work. We developed a test infrastructure for this thermal upgrade technology. You see in the back, just clicking, you see in the back, 2 large units, evaporator and condensers. They could be clearly smaller. The idea is that this infrastructure, you see just here, some yellow measurement units, and they actually measure the filling level of liquid water inside of these tube bundles. And we have a gas connection here. And here is actually the solid reacting material, our thermochemical reactor. So we can measure the conversion by measuring the fluid level inside of this condenser and evaporator. The whole system can be operated up to 320 degrees Celsius here with this thermostatic bath, and in absolute values between 10 millibar and 6 bar water vapor pressure. Very quickly, some results. We have a charging temperature here in red at, let's say, 185 degrees Celsius. This is the heat transfer fluid temperature. And what you see in this diagram is this controllable reaction. So as soon as the valve is opened, the material immediately dissociates, is releasing water. This has to be condensed in the connected condenser, and you see the endothermal process is initiated and starting, and we have something like 15 Kelvin of temperature difference in order to drive the heat transfer to the chemical reaction. Of course, this can be changed. You could charge it at 280 degrees Celsius, initiate the chemical reaction again here at this point. Then we have a larger temperature difference because the temperature goes down. So now in this case, it's 50 Kelvin. Of course, this temperature difference defines the thermal power of our system, and these two values are shown on the top of these diagrams. In black, we have a, let's say, 400 watt power for this low temperature charging, and for this high temperature charging experiment, we can have 1.2 kilowatt as peak power. And of course, this also is shown in the rate of conversion or the dynamics of the reaction itself. So just to summarize all of our experiments there, we have, of course, the possibility to play with temperatures. The minimum temperature we have used was something like 180 degrees Celsius, and the thermal power, the maximum thermal power, was 1.2 kilowatt peak. For the discharging, same thing. We said, okay, let's say we keep the temperature constant. It's the same temperature, so there's no charging and discharging loss of the quality of the thermal energy. It's the same quality of the thermal energy after discharging. And in this case, of course, it's the best case for our system. You see immediately the exothermal reaction is initiated as soon as the valve is opened. We have more or less a temperature jump here, and this results, of course, in, again, 1.2 kilowatt of thermal power during the discharging process. It's even so fast that our measurement was a bit interrupted here and didn't work that properly in this moment. And of course, we could also now increase the temperature. We have now 280 degrees Celsius. That's discharging temperature. It's useful temperature for our process at the end. We have a smaller temperature difference again. So it's slightly smaller thermal power, but we have almost full conversion. So summarizing all our discharging experiment, the temperature is adjustable, as I said, from 180 to 280 degrees Celsius discharging temperature. So in principle, we can have 100 Kelvin of temperature lift inside of our thermal store without any additional pump. The thermal power is more or less the same like for the charging process. For further reading, my colleague Jana Stengler, she finished her PhD last year, end of last year, and she published two, from my understanding, very interesting articles, Applied Energy in 2020, and very recently also one in International Heat and Mass Transfer. So if you are interested in that, please have a look. One word regarding upscaling. This is the reactor we have shown you the results. Normally, we have the problem with these thermochemical reactions that we have the heat transfer and the gas transfer, right? And this upscaling of these reactors is always a bit tricky. Either you improve the heat transfer or the gas transfer, so they are not normally not independent from each other. The concept behind this storage principle is that we only have the gas transfer in radial direction here, so we can make longer tubes and we can have more tubes. The gas itself is distributed pretty easily inside of the shell. Okay. And this is what we have investigated. This is now the last result. Basically, in the beginning of last year, we have started with the experiments. There, 4 tubes, 3 times longer tubes. We have connected it to the test rig I explained before, and it works perfectly. The publication is now in preparation, but it's not directly scalable because the heat transfer fluid was not really able to transfer this like 5 kilowatt of thermal power to take these 5 kilowatt and maintain constant temperatures. So we have to work on that. Okay. So far, this is a thermal upgrade. I said at the beginning in the contents, I want to just give you quickly an information who we are and what we do besides these thermal upgrade technology. This is the group thermochemical systems in normal times when distancing is not the main topic. We work on these, I called it advantages or thermochemical features of thermochemical systems. So of course, we address long-term storage possibilities with cheap materials, for instance, calcium hydroxide for even seasonal storage. We talk of preheating components for automotive applications, for instance, fuel cells. We try to utilize also this right side here of these thermochemical systems, so the generation of cold. I was talking about thermal upgrade of waste heat. This was the part of the presentation. Since we can have hydrogen as reaction gas here, we try to find synergies and to use synergies between hydrogen as energy carrier and hydrogen as a reaction gas for these thermochemical systems. This is of course important in order to reduce the complexity of the later complete storage unit. And we have some topics where we do not try to adjust the reaction temperature, but where we try to adjust the pressure, so the y-axis, for instance, in order to control the heat transfer through vacuum panels or something like this. Why am I saying that? You are highly welcome to join, to start an exchange with us. We are open for students, postdocs, scientists. If you want to visit us, you're highly welcome. And regarding any potential cooperation, we start with the characterization of the storage materials. We do not develop the materials itself, so we are always searching for partners that have a certain material, and we can bring it to a first technical concept. Characterization is important to differentiate between chemical properties and of course the physical properties, and all this is then as input into simulation work, of course, and the experimental validation or proof of concept, depending on the project itself. With this, I would like to summarize my talk. I hope I was able to introduce you my view or our view on thermal energy storage and the role of thermochemical energy storage in this field of high temperature thermal energy storage. It's clear that there are certain advantages of these thermochemical systems. I would say it's important that we focus on these advantages because they cannot or can hardly be met with other physical storages. Besides the high energy density, the controllable heat release, I hope I was able to introduce you this concept of adjustable reaction temperature. With this, I would like to thank again the organizers for inviting me. I thank you for your very kind attention. I'm looking forward for questions. Of course, I would not like to forget my colleagues that actually do the work in the lab and in front of the computers. Thanks a lot. I hand over to you, Richard.
Yep, thank you very much for the presentation, Mark. It was really excellent and very interesting. So we've got around 15 minutes for questions now. We haven't had any questions in the chat. I don't know if anybody would like to ask a question now. Hang on. So one is it's just come in. I don't know if you would like to read this out yourself or if you would like me to read it out. So this is Wei He, if my pronunciation is correct. I can read this out myself. Okay, so the question, Mark, is surrounding your the tree-like shape, you know, the fin structure, and just how you determined or optimized that shape. And the secondary question on what method, I assume that's manufacturing method, do you use to get that shape when you build the pots?
Yes, it's a good question, and the very frank answer is that for the reactor I have shown, we just use the expertise of our colleagues from the PCM and said, okay, as a starting point for our work, we do not need a perfectly optimized, let's say, fin structure and reactor structure. We want to have a proof of concept And then what we did, of course, is using a console FM tool to understand what is happening there. We have some thermocouples inside at different positions. And I think we have pretty good understood. One of these publications from Jana Stenger is actually also focusing on how could we improve the thermal power, for instance, based on this given concept. I would say this is state of the art how we approach that. But I like this question because there are, of course, possibilities to think of very fancy new geometries. Right? And how do we get to these very fancy and new geometries? What we do in parallel, but not for these high temperatures at the moment, is trying to find some optimization tools, theoretical, analytical optimization tools, and then use these additive manufacturing with aluminium. This is mainly done for metal hydrides at the moment, in order to see if this is true. The challenge, if this is really a battery reactor, an optimized reactor, the challenge there is always that this filter has to be, depending on the material, very fine. And so this is something which is not so easy to integrate in any fancy geometry of the reactor. But I would say, yes, at the moment we focus on, let's say, given proven heat exchanger structures that we adapt to reactors, simply because we have no manufacturing possibilities that are available at the moment, at least for us. And for the metal hydrides, we have since 1.5 years first steps into using additive manufacturing in order to have more freedom also for the manufacturing of these units. I hope this answers the question.
Yep. Well, I personally think that was quite a comprehensive answer. I do have a follow-up myself. I think you mentioned in the presentation that you struggle for thermal contact between the fin structure and your well, I guess it's like a packed bed almost. I suppose you have to try and find a balance between mass transfer through the bed and contact for heat transfer. So what is the main challenge at the moment? Is it mass transfer of what I think was water vapor into the bed, or is it the heat transfer through the bed from the fin structure?
Richard, I'm not sure if I mentioned that, yeah? But you're perfectly right that the contact between the bulk and the fin is something we cannot predict at the moment, because we have these structural changes in all of the materials I was shown. This is the drawback I missed in this presentation. But it's good that we go into these details. So the structure is changing with cycles. And this is, of course, an important work we do in order to understand how the structure changes. This tungsten bromide at the beginning, if you fill it in, it's a loose powder. And after 10 cycles already, it's a porous solid, which is still reactive. In the design we have, we see no degradation, at least from outside in terms of power. But when we open it, we see that this porous structure is breathing. Right? The volume change between hydrated state and unhydrated state leads to reduced thermal contact on the fin.
Okay.
This is actually part of this publication from Jana Stenger. And I would say if we want to improve this type of fin structure, we have to better understand what is the final status of this material, I would say, after 20 cycles, and is it then only breathing, right, expanding and shrinking a bit. We had measurements up to 1,000 cycles where we have proven that it's kind of breathing then, but this is ongoing work.
Yeah. Okay. Thank you. So next up, Adriano's sent me a message saying he's got some questions to ask directly. So Adriano, if you would like to unmute and ask a question.
So thank you very much. I'll take just a few moments because I see there are other questions in the chat. And one question was already answered about the, let's say, interplay between mass transfer and heat transfer in the geometry. Perhaps I'll ask a question more from the applications side. Have you looked at any specific, let's say, use cases in, let's say, energy-intensive industries of these, let's say, thermal storage / upgrade technology? Where do you see the sweet spot from also, let's say, techno-economic point of view?
Good point. Yes, we had two larger projects, nationally funded projects. This was with Evonik and Siemens. The idea was these two companies, one focusing on chemical industry with some batch processes there. Could we use this technology for batch processes, right? And for Siemens, the idea was, could we have it as, let's say, topping cycle or so for high temperature heat pumps at the moment, where the level is probably 150, 160 degrees Celsius. The problem we observed there is that it's a challenge, right, to find the perfect solid material at the moment, right, that fits exactly to the demand of this batch process or of this heat pump process. The application we had in mind, which fit quite good, was a paper industry, paper bulk production, where they have a huge amount of steam, which they use in order to cool down this paper. I think it's called slurry. At around about 150, probably 160 degrees Celsius. And now we have the problem that something like 15 kelvins are missing. So we should have had a slightly lower charging temperature, but this transfer bromide is not possible there, at least not if you say the condensation to the ambient is the reference. Of course, you could say we use a cooling system or so in order to go down with the gas pressure, but of course this is then from a technical point of view a bit difficult to explain, let's say. Yeah? So Adriano, the idea was having either batch processes or the topping cycle of high temperature heat pumps at the moment.
Thank you very much. Thanks.
Okay. The next question is from a S. Brielmeier. I hope that's the correct pronunciation. So he or she is asking, and it's just about the understanding of the principle of thermal upgrade. So the question is, if we have waste heat, for example, at 150 degrees C, are we able to discharge this at a higher temperature due to the change of pressure in the system?
Yes, I hope, yes, exactly. I hope I was able to make sure that it's like if you buy a car, right? You can say, okay, I have this acceleration, this, power level, and I have this consumption of, let's say, gasoline, that these two values are not always, let's say, in accordance, right? So we can have a temperature lift of 100 Kelvin. This is true. This is what we have demonstrated. But of course, for the sake of the thermal power of the system itself. Yeah, so this 1 kilowatt I was mentioning, we need a larger temperature difference. This is because of this distribution of thermal energy we discussed already. So this is the idea we want to go, improving these fins, having less temperature difference necessary for a certain power level. But in principle, of course, you're right, from 150 to 150. And this 150 is actually the pressure increase, or the temperature which is necessary to increase the pressure from this 100 millibar to, let's say, 2, 3, 4 bars of water vapor.
Okay, thank you. So we have another question in the chat from Alan Ruddle, who asks, which of the technologies might be suitable for use in an electricity storage system? And he gives the example that Siemens have a test system which uses hot rocks to store thermal energy. So if you just would like to make a general comment on which you think is most suitable for electricity storage, or well, indirect electricity storage, I suppose.
Yes. Thinking of these advantages, I mentioned in the beginning, I think it's clear that these two sensible storages have the advantage of a bankable, proven, in principle, almost ready technology to implement in such storages, or in such electricity storages. I think that the PCM technology has some advantages if you think of integrating heat pumps there, that you have a higher round trip efficiency, electricity to electricity, this Carnot battery topic. I would say for the thermochemical, we had a publication last year, Michael Lutz. If you're interested, you can just contact me. If we have another possibility to develop a thermochemical electricity store, I mean, from outside would be the same, looking the same, but internally would be totally different, I would say, regarding these large applications, storage for 1 day or so. I think the first 3, the physical storage technologies, are of course the choices you have, I would say, and this later on depends then on the process of your, let's say, power generation, which of these 3 is the most promising. If you have interest in, let's say, more details there, just send me an email. I can distribute it within DLR. There are plenty of experts that are happy to help you with these questions. I saw also Andre Tessis in the audience. He's of course expert in this field as well. He's the head of the institute where I look. So please just write me an email, and then I can distribute your questions to the right persons.
Okay. So Alan's just thanked you for the explanation there. So I don't know if anybody else in the audience has a question. You can take the opportunity to unmute and ask it directly now if you like. We've still got around 5 minutes. If not, I've got one final question myself, which is probably quite a simple question, really. But in my mind, at least, I've always thought of thermochemical heat storage as very much a long-term solution, you know, for long-term energy storage, perhaps seasonal energy storage. But I get the impression that the systems you guys are working on could very much slot into, you know, shorter scale energy storage systems, perhaps in a process plant, for example. I just wondered if you would comment on where you see the future, I suppose, for thermochemical storage.
Simple question, you introduced it, right? No, I think for my understanding, if you talk about a physical thermal energy store, I mean, you have to store, you have your heat transfer measures, and basically that's it. So the thermochemical storages, they are always a bit more complex. You have to have these gas handling. And I think the interesting aspect is that this gas handling is, let's say, if you have a black box, it's always a drawback. It's a more complex system or so. But if you have gas available, steam available, or hydrogen, as I mentioned, available, you can have these, let's say, combinations, right? Including a thermal store in a process. For instance, preheating fuel cells is one of the topics we are currently working on, also with these additive manufacturing of the reactors. So there are specific applications, and I think if you want to search for these applications, think of pressure. Where is a reactive pressure available? Water vapor, oxygen, for instance, carbon dioxide or so. And then it depends totally on your integration idea into the process itself. If none of these advantages I was mentioning, long-term storage, your concept, of course, controllable heat release, higher energy density if you do it in a right way, and this temperature change, it gives you any advantage for your process, I would always go for physical storage technologies. They are much more simpler, and of course at the end, very likely they're also cheaper and more bankable. So I think we have to fight for some specific applications. We have a couple of them. This is clear, but there are also plenty of applications I would exclude thermochemical storages.
Okay. Yeah. Thanks for that answer. I appreciate it. It was a bit of a difficult question actually, but yeah. Thanks a lot for that. Okay. So I think the questions have dried up a little. So in that case, Mark, I'd just like to thank you again for presenting today. I found the talk very interesting, and I'll certainly be following up, reading some of your papers, I think, and I'm sure others in the audience will as well. So so thank you very much.
Sure, thank you, Richard. I stop now sharing, right?
Yes, please. And Adriano, I don't know if you'd like to start getting your slides ready, please.
Yes, thank you very much. Let me just share my screen, my presentation actually. So let me know if you see in full screen mode.
Yep. So I'll just briefly introduce you, Adriano. So Adriano is actually the organizer of the event today as well. So I've agreed to chair in his place, just because with him being one of the speakers as well, obviously. But Adriano today is going to talk about high temperature latent heat thermal energy storage. I guess you're going to present a lot of the work that's being done at Birmingham today, Adriano.
Yeah, no, thank you very much, Richard. That's indeed the case. So, well, welcome everybody, and thanks for joining the webinar also from my side. I might actually at some point stop the camera. I don't have a great connection at the moment, but hopefully things will work well. So yeah, I'll spend the let's say time slot in the presentation here to present some of the work we have been doing at the University Birmingham, with a particular focus on high temperature latent heat thermal energy storage. So obviously this work is let's say an effort of quite a few people, and a few of them are here reported in this slide in my team. So I'll just brief outline of the presentation. So I'll actually introduce the let's say the institute and the center, which I'm part of. And I have a two-part presentation. One is on the actual the specific application of high-temperature PCM latent heat thermal storage for grid-independent combined heat and power system. And a second part, which is more on a methodological part about designing these high-temperature thermal storage system, and in general heat transfer enhancement in these components. And obviously, we'll wrap up at the end, and then looking forward to your questions. So let's say taking inspiration from Mark. So who we are. So I'm part of the University of Birmingham Center for Energy Storage. This is a cross-campus initiative that started in let's say toward the end of 2013, with two main let's say areas of interest or research around thermal energy storage, both on the hot side and on the cold side. And we are pretty much, let's say, driven by the let's say end use of thermal storage. Although we obviously let's say look at the basic in research needs that needs to be let's say unlocked to move from material scale to the system integration of thermal storage systems. And this is, let's say, the core of the activities of the center. Although over the last 7 years or so, it has expanded obviously in a few other areas. And as we have also discussed in the previous presentation, a key aspect about thermal storage in general is to think about the, let's say, its end use, and what a specific technology or specific thermal storage technology can bring to the table in terms of benefits and techno-economic, let's say, pluses compared to the system without storage. And therefore, that's the reason of expanding also beyond the let's say the technology development into the actual let's say process integration and system level application of storage. So we are some of you might know already, or knows quite a few the academics involved in the Birmingham Center for Energy Storage, but there are, let's say, 5 academics which each one of us has let's say leads a team of various sizes and dimensions, so to say, and overall we are 60 plus essentially center at the University of Birmingham, and with dedicated lab facilities and let's say experimental facilities for the, let's say, for covering those 3 scales in the development of thermal storage systems. So from let's say material characterization, and you have some examples at the bottom in terms of what is available in our labs, up to let's say lab scale prototyping and demonstration at lab scale. And obviously, if you are interested to know a little bit more in what specific let's say equipment or let's say lab technique we have, and that might be helpful for your research, please feel free to contact me, and we're happy to give more details. So regarding, let's say, the more scientific let's say content of the presentation, obviously I will focus largely on latent heat thermal energy storage, and we have, let's say, heard from Mark quite a bit of very nice, interesting, let's say, neat way to classify technologies for thermal storage. Let's say, focus of this presentation will be on latent heat, which in a sense at high temperature has also challenges that are relevant for a purely sensible thermal storage system. So what you will hear in part of my presentation probably also applies to a certain extent to sensible thermal storage system. Somewhere, let's say, arbitrary, but let's say for the context of my presentation, essentially the applications you will hear about are for 300 degrees C or above. Obviously, the great advantage of let's say, advantage of latent heat storage is to exploit this, let's say, physical transition, as we discussed before, and take advantage of the latent heat fusion of the material itself. And obviously, if we are operating across a certain temperature range, given an application, it's often important to also take into account the sensible contribution, which might not be necessarily negligible, and it's often relevant to be taken in consideration. So the let's say the results of what I'm presenting is let's say part of the outcomes of three main projects which my team has contributed or is participating here. So three of them, one is from two of them are, let's say, funded from UK let's say funding streams. Solar Turbo CHP project, it's a academic/industrial project. I will discuss that later. Then EPSRC based project, so from the Research Council. This top add PCM looks at actually topological optimization for thermal storage and how to identify optimal geometries for thermal storage system, and some aspects of let's say system integration or thermal storage integration in a European project which looks at business cases for waste heat recovery and how technologies can enhance the opportunities for recovery of waste heat. And one of these technologies is thermal storage indeed. So I'll dive into the first let's say project and give you more details about what we are trying to do in this project. So this project is a joint effort in collaboration between UK partners. We have Brits Energy and Samad Power, which are SMEs in the UK, the University of Birmingham, the University of Cranfield, and crucially, the University of Pretoria in South Africa. So this project is within a stream of funding that looks specifically at developing technologies for the sub-Saharan context. And here we are developing essentially a small-scale air Brighton system for combined production of electricity and heat. So what you see here on the right-hand side is let's say an early version of the prototype of the optical system that is developed at the University of Pretoria in South Africa, where essentially let's say dish concentrate solar energy in the focal point or in the receiver, approximately at 900 degrees C, and the heat of the solar thermal energy is used to drive a small-scale CHP system based on micro gas turbine. Is a recuperated system, so you have a recuperator here at the top, which is a crucial component in the let's say in the efficiency of the system. And obviously, given that the primary energy input is solar energy, one of the key aspects of this project, which is the focus of the work of the University of Birmingham, is high temperature storage of thermal energy. So the original idea was to use essentially the cavity of this system as both a combined receiver and short-term thermal energy storage system. So one of the key let's say challenge of this system is the sensitivity of operation due to the let's say operating point of the micro gas turbine, as well as indirectly of the compressor itself. So maintaining inlet conditions and the turbine as close as possible to the design conditions is one of the key aspects to produce, let's say, performances that are as close as possible to the nominal one. So here we are talking about a system that has, let's say, opportunity to produce power output up to, let's say, 10 kilowatt electrical and about 40 kilowatt thermal. So the idea of using, let's say, high temperature phase change materials initially was to smear out, let's say, the short-term fluctuations in solar thermal energy input, so that ultimately the inlet temperature of the turbine is kept as constant as possible. So as I mentioned before, the let's say solar thermal energy concentration occurred at about or implies a temperature at the receiver here of about 900 degrees C, or between, let's say, depending on the process layout, between 700 and 900 degrees C. So the original piece of work we did together with the University of Pretoria was to sort out possible candidates for PCMs that are ideally placed around the coil that is within the receiver. Within this coil, there is the air that is processed through the system, so that the, let's say, passive effect of the PCM that is around the coil essentially produces a smooth temperature output of air at the outlet of the receiver. And so a key aspect here is to have obviously a PCM or temperature that operates at temperature that are compatible with the system. So we're talking about 900 degrees or so, and as well as a fast response, given that we try to essentially to smear out fluctuations that are of the order of perhaps 10-15 minutes. So the initial work looked at a quite challenging, as I will discuss, type of PCM, so metallic PCMs, because also compactness is quite crucial here. This system is mounted on the arm of the solar dish, so compactness is a clear requirement here. So what you see here in this slide are the, let's say, initial candidates that we look at to, let's say, deliver this high temperature thermal storage functionality. And I broadly split them in two areas. Those that were more favorable from operational point of view, essentially for a higher operating temperature. And we have a series of metal alloys, particularly silicon-based metal alloys, which obviously pose some clear challenges, which I'll discuss later, but are favorable from operational point of view. On the other side, let's say on the slightly lower operating temperatures, still relatively high for the general consensus about high temperature thermal storage systems, where let's say some commercial actually molten salts, and on the lower end side pure metal. So these were let's say slightly more favorable from actually preparation point of view, and ultimately let's say manufacturing within the thermal storage component compared to the one on the right hand side. So the let's say initial work that was done looked at sort of multi-criteria decision analysis to meet the specific requirement of the application here. So obviously there is the typical requirement of weight constraints and compactness, which hopefully the latent heat of the PCM contributes to achieve. But this system actually tracks the let's say solar position during the day. So actually here we have a thermal storage system where possibly slosh dynamics occurs. Slosh dynamics refers to essentially the movement of the PCM when it's in the liquid state due to the movement of the arm of the solar dish. And as I mentioned, the coupling between the operating conditions of the various components, and potentially also some obviously risk of failure given the harsh operating conditions. So we look at various operating let's say parameters or perhaps criteria to let's say meet the final requirement of the application. And ideally, initially we were preferring to actually use a pure aluminum as a PCM, sacrificing to a certain extent a little bit the operating temperature, because the melting point of the aluminum is in this context relatively low, but let's say more favorable in terms of material as option to ultimately build and manufacture in a let's say cost-effective manner the components. And I'm not going to obviously let's say cover all the criteria that were looked at, but I would like to actually touch upon 3 of them that probably are quite relevant in the domain of high temperature thermal storage and what we have let's say investigated in this sense. Particularly compatibility is a crucial aspect. So compatibility between the PCM itself and the containment of the PCM. Volumetric expansion due to the change in density between the PCM at liquid state and solid state, another aspect that is sometimes, let's say, overlooked in the area of thermal energy storage, let's say, research. And, well, as I mentioned, also the containment itself, which needs to be compatible and needs to be able to accommodate the volumetric expansion. So one of the key aspects in this domain, in this type of application of high temperature thermal energy storage, particularly with PCM, is that in general, I would say that oxidation is fundamentally problematic, regardless this choice of PCM that we are considering here in terms of metallic PCMs, given that essentially oxygen forms compound with all the non-radioactive elements on the periodic table. Metals and metalloids are particularly relevant here. So one of the, let's say, elements we haven't, let's say, covered, or we are not covering at the moment in this project, but I think it's a good element to be considered, is generally the greater degree of freedom that would be allowed if environment, so the PCM is an actual inert environment. So here we're talking about using inert gases that might actually surround the PCM to prevent oxidation problems. In general, another crucial aspect was and is the goal to achieve or to avoid chemical changes and evolution in the containment structure. And there are, I would say, 4 key approaches. A couple of them are always in people's mind. Some others are not necessarily always considered as they should be, in my view. So to avoid essentially degradation of the containment due to the interaction with the let's say, molten melted PCM, I think there are technically four approaches. So thermodynamic stabilities. So here we are looking at possibilities to have the possibility to have the essentially a combination of PCM and containment that ultimately has Gibbs energy of approximately 0 at the operating condition. So it's inherently thermodynamic stable, and there are a couple of examples in the literature in general. Presaturation, this is essentially alloying or mixing the PCM with other components to prevent essentially further dissolution during the operation stages. And then the more, let's say, common, or let's say those that are used more commonly, transport limited steps, which essentially are coatings in a certain way. So here we are trying to minimize these degradation of the containments by essentially playing with Fick's law and reducing as much as possible mass transfer phenomena. Although we have to remember that in general, the diffusivity coefficient increases exponentially also with the increase in temperature. So at some point at high temperature, also this approach might fail or might not be as suitable as required. And ultimately also essentially limiting the reaction steps, but also here let's say reaction constant is typically a Arrhenius type of reaction constant. So at high temperature there is it's more challenging to obviously limit these reaction rates given the exponential behavior that they have. And here we have a typical example from the literature from molten zinc with the stainless steel containment, and you can notice the let's say estimated corrosion rates here. We are talking about something that it's incredibly fast. We are talking about 5.5 millimeters of thickness of stainless steel that is corroded per year of operation. So obviously this doesn't let's say comply with the typical life requirements of thermal storage application at high temperatures. Another aspect I think is important to consider, and that not necessarily is always the priority list in when high temperature thermal storage systems are developed, is actually the volumetric expansion of PCMs. Let's say in this case metallic PCMs at high temperature. Typically, depending on the metal considered or the alloy considered, we have volume changes that might be between 2% to 6%, which might ultimately lead to cavity formations during the solidification and melting process, and also to obviously stresses in the containment, as well as potentially high temperature fatigue. However, there are also some, let's say in general, the PCMs shrink from a liquid state to a solid state, so we have a volumetric reduction. However, there are some interesting exceptions to this case. So materials with ionic or covalent bonds do actually expand. So silicon alloys might actually expand during solidification. And another key aspect to consider is actually the interaction between the PCM and the containment material. So we might have kind of behavior where the PCM do not, so to say, stick to the wall of the containment. So the shrinkage is actually favorable because the PCM doesn't remain in contact with the containment, which prevents or facilitates the reduction of stresses that might be induced. Or the opposite situation, we might actually have, let's say, adhesion between the PCM and the containment, and especially if we have also, let's say, expansion during solidification, that certainly leads to volumetric or to stresses in the containments, which are obviously challenging, especially at high temperature. So that's a clear, let's say, aspect that needs to be considered during the development of a high temperature application of latent heat thermal storage. So interestingly, these, at least in the context of the project that we are developing here, things moved along during the let's say, development of the project. So as we actually explored the initial application of thermal storage, the underlying work in, let's say, techno-economic analysis from partners, as well as the high risk posed by the high temperature application, shifted the interest toward actually a slightly lower temperature thermal storage application. So instead of being fully integrated in the solar receiver, here just say with a slightly different schematic, let's say, economic case for this application led to actually reconsider a slightly lower temperature thermal storage that is recovering essentially the heat wasted from at the outlet of the recuperator at be around 300-500 degrees C, and this heat can be then later on essentially delivered to the end user during nighttime. So from a shorter scale duration storage for fluctuations, we moved to slightly longer duration storage application for intraday storage of heat for, let's say, provision of heat to the customer at the end point of application. So depending on, let's say, the couple of different configuration of the upstream process, we had a couple of different possibilities. So as I said, depending actually on the receiver configuration, application at around 300 degrees C and another one around 500 degrees C. And this obviously still remains in the domain of what I will define high temperature thermal storage. Opens certainly much more applications or let's say opportunities for material selection and design of the component. And well, this slide kind of comments on the benefits of having the let's say repurpose the application of the thermal storage system. Probably here one of the messages maybe I would like to pass across is that it's important to let's say conceive the application and the, let's say, development of the actual thermal storage unit quite closely with the let's say intended final application, and perhaps with the more economical and techno-economical drivers that ultimately lead to the greater benefit of the thermal storage application. So having this storage here on the, let's say, on the back end of the process leads to essentially an increase of the overall efficiency of the system with the recuperation of part of the heat that was wasted. The thermal storage can be essentially retrofitted and decoupled from the other high temperature components. This adds increased flexibilities in the operation of the thermal storage unit, and also reduces, as I mentioned, the risk, the technical risk. And furthermore, the original requirements in weight and volume constraints were eased, because here now we have a storage system that can actually be installed, let's say, on the ground, is not anymore integrated in the receiver, and therefore we can essentially have a larger system for longer duration of longer, let's say, storage duration. So obviously we carried out let's say the more numerical analysis of the actual performance of this component with a couple of let's say material options here. So here we look at pure metals as well as conventional molten salts, or actually, let's say, mixtures of molten salts. And we have obviously look at the dynamic of the charge and discharge of this thermal storage system. So when the storage was now replaced at the tail of the process, we had opportunity to work with a storage duration up to 4 to 6 hours during charge, and about 2-3 hours during discharge. Here, the blue line represents, let's say, a synthetic inlet temperature to the thermal storage, and that was, let's say, used in the modeling work to predict the charging dynamics and the discharging dynamics of the thermal storage for actually both of the materials selected. So the top figure here was for a melting point of around 500 degree Kelvin, and this, the bottom one at around 700 Kelvin. And you notice the typical, let's say, behavior in latent heat thermal storage system, where the let's say the phase of charging, which moves from liquid fraction equal 0 to liquid fraction equal 1. So during the actual melting of the PCM, leads to a nearly constant operating temperature of the PCM itself, or as well as the outlet temperature from the thermal storage unit. On the right hand side, you have a couple of indication of the typical metrics we have used for this let's say repurposed application of the storage system. So where we are at the moment, also in close collaboration with the people at the University of Pretoria that are part of the project, are this experimental testing at let's say kilogram scale, if you prefer, of the options that we are currently considering. A couple of molten salts that are actually commercial products at the moment are typical so-called solar salt, which is a binary mixture of salts. And on the material, we actually tested, we've been testing aluminum as well as zinc, where the zinc option has to, let's say, be developed also with the need of specific coatings for the components to obviously prevent the corrosion issues I mentioned before. So even though this is a slightly lower, let's say, lower temperature application than the original one, let's say the challenges remains quite relevant, although they're more manageable, as I mentioned initially. So we carry out the typical characterization and the experimental testing at the University of Birmingham. Is with the typical package of characterization techniques, such as the thermogravimetric analysis and differential scanning calorimetry. And one of the interesting aspects here is that probably is also sometimes overlooked during the development of this type of storage unit is the material preparation at the scale relevant for the final application is also quite important, and presents some non-trivial aspects that might not be let's say so evident when we perform purely testing at material scale. So this gives you an idea of the let's say salts options and how they essentially look like when tested in our facilities and in our labs. It's interesting that both of them, which are essentially a mixture of salts with slightly different operating temperatures. So this, what you see here is essentially a nominal operating melting point of the salt, needs a careful pretreatment to actually deliver the let's say expected thermophysical behavior. And this is relatively easy to be carried out let's say at lab scale, but when we think about scaling up the application to hundreds of kilograms, needs to be, I think, carefully planned, and it's part of what I think we will find out in the following stages of the project as well. So just to give you an idea of what I'm let's say referring about here, this is a typical DSC analysis of one of those materials candidates for our application. And you notice here the typical peak in the DSC signal that is essentially the one that we are interested in to use the latent heat of fusion of the material. And although you might notice here on the left-hand side a series of, let's call them side effects, not necessarily side reactions, that occur when the material was tested as delivered, so without pretreatment to essentially understand how it would behave if it wasn't initially treated from a thermal point of view. So it's important to not forget that we might have quite a few side effects at high temperature, and that needs to be essentially carefully, let's say, removed with a pretreatment of the material eventually. And neglecting these aspects might obviously lead to unexpected behavior at the component level if not taken in consideration at the very beginning. So how the unit will let's say look like in the project, we are looking at a relatively small scale demonstrator to have ultimately a demonstration of the whole solar turbo CHP system in Pretoria with all the components, so receiver, recuperator, the microgas turbine, and the thermal storage system, as well as the compressor. So we will essentially look at a small unit in the order of 40 to 50, let's say, kilowatt hour. That is actually a modular unit. So what you see here is a dedicated, let's say, pipeline, which will be included in the containment of the thermal storage unit, where the PCM will be placed initially without any specific heat transfer enhancement measures, which I will discuss actually later. The reason of using actually these slightly unconventional configuration is that these are originally, let's say, iteration of the original concept that was the thermal storage fully integrated in the receiver, and also allows to take to account precisely of the very strict pressure drops constraints that we have in the application. This system will be installed, let's say, at the tail end of the other components. So we don't want to have, let's say, effect of back pressure at the turbine, which actually will affect quite significantly the performance of the microgas turbine. So that's the configuration here is a compromise between, let's say, heat transfer performances of the device, as well as meeting the pressure drops requirement. Then we are obviously in the stage of analyzing how this component operates as a whole, and this is a typical, let's say, CFD predictions with this case with zinc option, and this will be bring the next phases to basically manufacture and installing it for the final demonstrator, which hopefully will occur in the next year or so, given or taken obviously all the other constraints in the world today. So this brings me to the point where let's say we have covered the materials and as well as some specific challenges that there are in material selection in use. And the next part of the presentation, I will spend the next 10 minutes or so in discussing a little bit more how the configuration of thermal storage systems in general can be optimized, and what are the, let's say, tools that we have been developing to optimize configuration of thermal storage system with latent heat configuration. So in the second part, part links to what we have heard also from Mark and from questions from the audience. So we'll discuss about the topological or a method that is called topological optimization for in this case performance maximization of latent heat thermal storage system. And these are presented some of the ideas and work we have been doing over the last, I think, 4 years or 4 or 5 years, and how, let's say, what sort of framework we have been using to maximize or to design thermal storage units and some part of thermal storage units. So in general, the let's say the selling point, if you prefer, of latent heat storage unit is that they are, let's say, energy dense, probably compared to sensible storage system, but low power density. In other words, let's say the charging and discharging rate might be dramatically affected by thermal conductivity of the PCM, which in quite a few cases is relatively low. So the process of charging and discharging becomes driven by heat conduction. So the need is to either increase power density, so increase at a certain point in time during discharge the power density, or for the same, let's say, for a same duration of time of discharge time, achieve a higher average power output. And obviously, as we have also discussed before in the previous presentation, there are quite a few strategies here. various, let's say, elements or heat transfer enhancement techniques, essentially fins and, let's say, structures that are at the interface between the heat transfer fluid and the PCM. So what you see here, let's say, some schematics of what is available in the literature of fins used to enhance heat transfer between a working fluid and the phase change material. So the typical approach that is used here in the literature is essentially parametric optimization, where an actual configuration is decided a priori, and then the parameters of the configuration are modified to obtain, let's say, the best optimal configuration for that specific topology, specific design. So what we have worked on was to essentially get rid of these initial constraints in the optimization of thermal storage units. So moving from away from parametric and parallel, let's say, parametrizations of different configuration, each one optimized around each initial configuration that were considered, to a so-called heuristic approach, where we try to expand the design space to all the possible options available, and have as an output of the optimization problem the actual topology of the fins, as well as their optimal parameters. Okay, so we want a methodology out of which the topology emerges as an output of the optimization and is not actually decided a priori at the very beginning and then optimized. And this is where, let's say, topological optimization come into place, which technique that originally was developed for let's say, structural mechanics applications, and we have, so to say, applied and tailored it for latent heat thermal storage units. So very kind of case study here, if you prefer, a single shell and tube thermal storage system with a single passage, and let's say in green the PCM that surrounds the heat transfer pipe. So here we are looking for optimizing the distribution of a certain amount of metallic material that should maximize the heat transfer between the working fluid inside the central pipe and the PCM. So here the design variable is actually the material distribution. So we are trying to shape this black blob in the best optimal way to maximize the power density of the thermal storage unit, or to maximize the heat transfer, if you prefer. So yeah, this is just a mathematical definition of the problem. So essentially we are trying to maximize the state of, or let's say minimize the state of charge for a certain given time of discharge, or equivalently to reduce the discharge time for a given end state state of the thermal storage unit. So I'm not going to dive into too many of details, also because I'm running a little bit short of time. But the idea here is to parameterize or introduce a so-called density approach, so a continuum variable that uniquely describes the presence of either the PCM or the metallic material in the domain. So this continuum, let's say, distribution allows to essentially track if in a certain location in the domain there is either PCM or the metallic material that enhances the heat transfer in the PCM. So in, let's say, in simple terms, white means PCM, black means the heat transfer enhancement materials, the material of the fins. And this can smoothly transitioning from 0 to 1 at each point in the domain. So this, therefore, is a continuum function, continuum variable, which we want to essentially optimize over the domain. I'm gonna skip the, let's say, the physics here. Just what I want to say is that the underlying physics of the problem becomes dependent on the geometry of the problem itself. So thermophysical properties here becomes function of the density distribution that I mentioned before, and that's why we can introduce them in an optimization, let's say, workflow, which is, let's say, summarized in this slide. So there are three main ingredients. There is let's say, the underlying solver of the physics, and in our case was a finite element simulation. The so-called computation of the adjoint problem. This gives the sensitivity, so how much the objective function changes compared to the let's say, density distribution, and let's say, update of that distribution according to the criteria of convergence. Till we obtain essentially the final geometry. So, and that's the so-called topology update, if you prefer. So, how these look like when it's implemented. So this slide will give you an idea of how the geometry naturally evolves from the definition of the topology optimization problem. So this is a cross-section of the system at the very beginning of the optimization work. We are not including natural convection, which I'll discuss later. So this is a uniform distribution of this density function at the beginning. And on this chart, there is the actual, let's say, convergence of the optimization work. So what you see here is the evolution of this density distribution function that naturally emerges from the topological optimization and leads to the optimal, let's say, configuration of the fins given the initial objective function. So this gives you an idea of, let's say, the ability of this topological optimization method to reach the topology, the optimal topology, without really prescribing an initial configuration. And obviously the design moves along various Pareto fronts. So what you see here is actually how the optimal design changes depending on what is the let's say state of desired final charge in the storage system. So for a system that has shallow discharge cycles, obviously we want to have fins that are pretty close to the central pipeline. And as we move to a system that has longer discharge times or depth of discharge that are bigger, the systems start to have fins that are more spread out across the domain. So perhaps I'll comment on the fins when natural convection is taken into place. This unit is let's say in horizontal position. So on the left-hand side, you have the topological optimized fins when only diffusion, here means heat diffusion, is taken in consideration, as well as the solidification process. However, no natural convection was taken in consideration in the melted PCM. And while if melting, let's say natural convection is included in the optimization workflow, start to see what are the differences. So the fins start to be predominantly toward the bottom part of this unit, because there is where the melting process begins, while the top part of the unit becomes, so to say, naturally or inherently, let's say, heat transfer is inherently enhanced at the top of the unit, because natural convection currents will start to occur from the bottom to the top of the unit. And well, this gives you a comparison of if these features, so including the natural convection, is considered in the topological optimization workflow that leads to, let's say, outputs or a reduction of let's say charging time that are quite significant if the fins are developed and designed with this type of configuration. Obviously, the process can be, let's say, can be also developed for multi-tube optimization or multi-tube configurations. I'm going to skip this and move toward my conclusions, essentially. What I would like to also emphasize here is that we can actually combine the material selection with the topological optimization framework. So what you see here are essentially the Pareto fronts of the optimization when we consider different type of PCMs, from conventional PCMs to solar salts and relatively, let's say, inorganic PCM, as well as with different materials of the fins. And this work was actually carried out with specific constraints in cost. And additive manufacturing was mentioned, so obviously one of the typical, let's say, possibilities, especially if we have complex geometries to potentially produce them with additive manufacturing, although obviously here cost constraints come into picture, but we have tried to develop or to test the geometries that were optimized and manufactured with additive manufacturing, metallic 3D printing. So this is how it looks like for a relatively low temperature PCM in a small device in our labs. So I'm going to move to the actual conclusion or contribution. So main contribution from, let's say, from this set of projects are this development of latent thermal storage unit for a combined small-scale combined heat and power system for temperatures that are around 500 degrees C for the final application. Key message is probably that the design and the integration of these high temperature thermal storage units it's quite crucial to have co-development with the, let's say, techno-economic drivers and needs, so that ultimately the system meets also the best, let's say, economics of the final use application. And also the topological optimization method can, so to say, unlock new geometries and let's say prevent us to use the usual, let's say, Finn's geometry and get rid of the initial assumptions that are usually made when geometries are considered to bring a thermal storage system at a higher performance levels. So I'll stop here, and I would like obviously to thank everybody for the attention here, and thanks people in the members of the team, collaborators, and partners in the various projects. And I'm more than happy to take questions here, as well as to provide more information if needed later on. Please feel free to contact me. And Richard, I'll give the floor back to you, and looking forward for questions.
Yes, well, thank you very much, Adriano. That was very interesting. I think you covered a number of different aspects there, which were certainly very interesting to me, and I imagine everybody else. I've got a few questions myself, but I'll open the floor to everybody else first, I think. So if anybody has a question, either put something in the chat, or you can indicate in the chat that you would like to ask a question in person, so to speak. Well, actually, while we wait for questions to come in, I'll maybe ask one myself. I was very interested in, well, in all of the talk, but particularly the second part. Thought that was really interesting. You know, the optimization of the topology. One thing I was wondering, and I don't know, I can't decide if this is significant or not, but is it possible to also optimize it axially, so along the length? So bearing in mind that the heat transfer fluid is probably going to be hotter at the inlet than it's going to be at the outlet. Is it possible to also optimize in the axial direction as well? I realize that the computational power will be quite large, but I just wonder if you want to comment on that.
Okay, so yeah, I've lost your question for a second for connection, but I imagine you were asking about not just optimizing the cross-sectional, but also in the axial direction, isn't it?
Yes, that's right.
Yeah. So, well, yes, one of the let's say key challenges there is obviously the computational cost of a fully three-dimensional topological optimization. We actually perform let's say an actual optimization in 3D with also the changes in the axial direction, which essentially took in consideration that you have a change in the temperature of the working fluid as it's passing and flowing through the pipeline. So essentially, you have a decrease in the roughly a decrease in the driving temperature difference between the PCM and the working fluid. So we have noticed let's say a change essentially in the topological structure as we move along the axis, but ultimately that led to let's say an improvement of probably 10% or so, further 10% or so in the discharge, in the reduction of discharge time, by accounting also for the axial topological optimization. One key aspect or challenge there is that this axial geometry is not necessarily connected. So it's not simply an extrusion of the initial one or an extrusion with a twist, but it becomes potentially a series of disconnected patches of metal that obviously becomes even more challenging in potentially, let's say, manufacturing or testing it experimentally. So that's why I think let's say the threshold between or the trade-off between computational efficiency and gains in performance was not, let's say, so let's say valid, if you prefer, for axial configuration or axial optimization. And this is actually, I think, if I remember correctly, reported in actually the first paper that we published on this topic, and is in the International Journal of Heat and Mass Transfer. I think it was 2018. So there is actually the three-dimensional geometry presented in that paper.
Okay, right. Thank you. I'm going to ask another question just because I'm quite interested in. This isn't the most practical idea I'll ever come out with, but in your optimization, you obviously had white areas which were 100% PCM, black areas which were the insert, and it was a sliding scale between, you know, white and black. Could you also optimize for, you know, using something like a metal mesh where you might have a varying density of mesh in each area?
Yeah, oh, that's an excellent question, and we actually did it, and it's is a little bit in a, probably for this community, in a little bit more obscure type of journal, because is in a journal that is quite let's say from computational methods. So I can definitely share that journal and that paper, which we have looked at essentially configuration of metallic, let's say metal foams impregnated with PCM, and how these let's say can be optimized. The challenge there is that you start to have well, two topological problems nested one into each other. So the let's say the implementation and also let's say the mathematical details are certainly not not trivial. But I'll have that piece of work is I can more than happy to share it with you. But we have seen we have applied for the same geometry here. So we thought about a single tube, a single shell and tube with PCM, and a metallic structure, metallic mesh instead of the fins. So your density function has to track the PCM and the metallic structure and ensure that it becomes a metallic fin. So it's periodic essentially. And we have seen similar effects where the metallic structure becomes, let's say, skewed or elongated in a certain direction, depending on the effect of let's say the solidification and also the natural convection. So for example, we have seen metallic mesh structure with the elongated cells, so quite thin on one dimension and quite long on the other one, and the long side is along the radial direction of the shell.
Okay, I'll not ask any more questions. I'd never came across that work before, so I was quite fascinated. But I'll not ask any more questions. I'll maybe follow up with you afterwards. There was a question during your talk from Peng Jia. It was about the first part of your talk, just simply asking why you didn't consider an aluminium silicon alloy, and particularly mentioned number 12, so aluminium silicon 12. If you had anything to comment on that.
So yes, so we have well, we have considered a range of let's say options. You can have a look back here, basically, which were these one here. So in our initial options, we have considered well these metal alloys, mostly from operating condition point of view, but also from some specific constraints we have in this project. So we kind of have a sort of cross section of various constraints, both the technical one, the available alloys, but also what is available locally in South Africa. So a few of the alloys that were used or that are, let's say, covered also in the literature were not available by local suppliers there, and therefore we discarded them initially, because let's say it's really this system needs to be, or the business case of this system, given this project is at the interface between industry and academia, needs to lead to, let's say, favorable cases at the location where this system is meant to operate, and therefore by potentially also driving let's say business opportunity, jobs opportunity for those in the industries related to the manufacturing of this project, we focus only on the alloys that were available ultimately at well in South Africa.
Yeah,
from local suppliers.
Yeah. Okay. Yeah, I think that's a comprehensive answer. There's another question in the chat from Benedict Shinku. It's quite long, but I think the question basically says, so you've looked at in the optimization of the storage system in isolation almost, but I think he's pretty much asking if you want to comment on how this would link in with a fully integrated system, you know, the optimization of the full system rather than the individual storage device.
Yeah, that's a very good question. So yes, at the moment, well, at least for what I presented here, we have looked at essentially having from the work also done by the other partners working on the microgas turbine and the overall cycle, the nominal operating conditions. And from those nominal operating conditions, those were used as let's say inputs in the optimization or in the selection and the design of the thermal storage system. And here is one of the points that I certainly would like to make is that we have seen that often the thermal storage units, the thermal storage system are sometimes considered as an afterthought. Okay, so the system and the initial upstream processes are developed, and then there is an attempt to retrofit the units, which leads to, I think, constraints on both sides. So the more the design is actually a co-design, the greater I think there are possibilities to unlock the benefits of having thermal storage systems integrated in a full process. But as I mentioned in this work, at least in the first part, is from the, let's say, design conditions and the requirements of the upstream components used as an input for the design of the unit. I might add that from the topological side, or topological optimization work, we are working on, let's say, an extended version of topological optimization that can couple the topological optimization at component scale with a broader, let's say, simulation of the surrounding process, so that we can take in consideration more realistic boundary conditions, if you prefer, into the topological optimization work.
Okay. Again, I think that's a very comprehensive answer. We've got another question from Alan Ruddle. It's quite a long question. Alan, would you be willing to ask that yourself? Because I feel like it's kind of 2 or 3 questions in one.
Yes, thank you, Richard. Can you hear me?
Yes, loud and clear.
Okay. Adriano, thanks very much for the presentation. I believe the system you mentioned, developed by Pretoria, is a standalone system, primarily at least. So it would be useful to be able to modulate the ratio of heat and power produced. Is that possible? And a second question would be, are there other options for the generator? And in particular, I wonder about things like thermoelectric generators. Are they just too expensive and inefficient, or could they be considered?
Yeah, it's thanks very much for your question. They are absolutely very good one. So yes, for the first one, it's intended to be a standalone system that potentially can be deployed co-deployed near the end user of both electricity and heat, potentially off grid, given also the let's say challenges that locally there are about load shedding and blackouts. So it's meant to be a standalone system. The decoupling between electricity and power, let's say, power generation and heat generation. So the idea, or let's say the final intended application of thermal storage there is an attempt to actually unlock this decoupling, in the sense that the heat that is produced typically during generation of power during, let's say, hours where there is solar irradiation is actually captured downstream the recuperator to be then delivered later on during the evenings when solar irradiation is insufficient to run the system. Obviously, it's possible potentially to envision or consider full decouple between electricity and heat production, a little bit with the use of storage, a little bit what is done in, let's say, large scale combined heat and power plant. Although we haven't, let's say, addressed these within the context of this project, but it's probably an interesting aspect to explore further. And last, let's say on the generation side, again we have looked at, let's say, original starting point was the preliminary work that was done on this system, on the actually use of microgas turbines that might be actually recuperated from other applications. So the original prototype had actually a microgas turbine that was, so to say, a microgas turbine from an automotive application. So we are looking certainly to have either components that are off the shelf or components that can be actually repurpose it from other end life, let's say, applications of other technologies. So we haven't, let's say, scanned all the possible options in terms of generator, but I would say that some of them, perhaps the, let's say, thermoelectric generator, so might not meet the let's say the cost requirements that are quite strict, obviously, from this application.
Okay, thank you very much, Adriano. Very
Thank
good.
you. Thank you for the question.
Sorry, I was muted there. Very quick question next of all, can we get a copy of the slides? We'll let you know about that afterwards. So I understand the recording of the webinar is going to go on the Supergen and Heat Transfer Committee websites, I think anyway. We'll ask the authors offline if they want to give PDFs of their slides as well, and if so, they'll be on the websites as well. You will get, everyone who attended today will get an email with the web link so they can rewatch the session. I think that's right, Adriano.
Yes.
But whether or not the slides are included, it will be at the author's discretion. And what we'll take as a final technical question is from Roger Moss, who asks about the electrical and thermal efficiency and how it might compare to PV or PVT solar collectors.
Yeah, so the let's say efficiency that we are targeting with the let's say with the prototype at the end, we're talking about let's say electrical efficiency that is around probably 18–20%, but this is mostly a let's say heat driven application at the moment. However, let's say probably an important point to make here is that we are not trying to necessarily compete with a combination of let's say PV plus batteries or similar type of combination that might produce electricity in a decentralized fashion. Again, for the constraints and for the specific let's say context of this project, we are looking at system and that can be essentially manufactured locally, and that the materials can be let's say either repurposed from other applications, and therefore can be also purchased, let's say, locally, and provide some sort of opportunities for businesses locally and jobs for local communities there. So in that sense, the let's say electrical efficiency might be similar, although probably we are seeing that the heat streams start to have a kind of greater value with the second type of application that I presented. But we are trying to, let's say, make the system as local as possible, and therefore we not necessarily try to compete with the PV or PVT systems, and to therefore also use more accessible materials.
Okay, thanks, Adriano. So with that, I think we've had quite a few questions, so we'll close the floor to questions. So I just want to thank Adriano and Mark again for the presentations today, which were excellent. Before we finish, I just wanted to give 2 or 3 slides myself just on a seminar series that we're going to be running as part of the Heat Transfer Committee. It'll only take about another minute of your time, so if everybody just bears with me for 1 second. So hopefully you can see this. Adriano, could you just confirm? Yep.
Yes, yes.
Okay, so at the UK National Heat Transfer Committee, we are going to be running an online seminar series. So I think Tassos at the very beginning mentioned that we were intending to run workshops on a kind of twice per year basis, but COVID-19 has destroyed that idea for now anyway. So we're going to replace this with some monthly seminars, which will be free to attend. At the moment, we've got 2 dates, but we will be running these monthly. If anyone in the audience would like to offer a presentation, just send myself an email. So myself and Francesco Coletti are in charge of organizing this. And, you know, we'd be open to having anyone present, as long as you've got some interest in research to present. Dates for your diary so far, next month on the 25th, Professor Sefian from Edinburgh University, who's also the vice chair of our committee, is going to give a talk on advances and challenges in droplets wetting and evaporation. So his work, if you're not familiar with it, is very interesting, and I would encourage everybody to attend that. A month later, on the 22nd of April, a colleague of mine, Dr. Jonathan McDonough, is going to give a talk on additive manufacturing. So he's going to talk about opportunities and challenges for additive manufacturing, both in heat transfer and in chemical engineering research. And yeah, we will continue this monthly. We've only got 2 speakers so far, but I'm sure we'll add more fairly quickly. We haven't actually had a lot of time to organize this yet. I just wanted to make an announcement while I had a few people present. If you're interested in any of these presentations or anything else to do with the committee, you really should join the mailing list, as that's the only way that you will get the information, I suppose. So that's just uknhtc.org. And I might just leave that web link on the screen while we finish up the session, if that's okay. So yeah, so I'd just like to finish up again by thanking Adriano and Mark again. Like I said, I've said numerous times, the talks were excellent, very interesting. And yeah, thank you. I'm sure everybody enjoyed it. Thanks to Adriano for organizing, and I'll hopefully see some of you guys again in a month's time at the UK National Heat Transfer Committee seminar series.
Thank you very much, Richard. And
yep.
Thank you, everybody. Thank you, Mark.
It was a pleasure.
Thank you.
Okay, right. Thanks, guys.
Thank you. Bye-bye.
Bye. Bye-bye.